Good morning, everyone. This is Bruno from FAMIC Technologies. Thank you all for attending the second webinar of our series on Automation Studio version 9.0. So let's get started. So to recap, this is the list of webinars that are planned for this series of webinars. We had our webinar last week, which covered the new functions. So that video is available on the webinar platform for anybody who's registered, and the videos will be publicly available on FAMIC websites once all the webinars are completed. So today we'll be going through this webinar here. So the new simulation features. This is going to include presentations on the new pneumatic grippers, some new mathematical blocks from our math workshop, and some new electrical components. So we'll be doing those presentations and then going through some Q&A. Again, for the questions, please feel free to use the questions box during the webinar. So we'll try our best to answer all your questions during the session, but then we'll be covering them at the end of the session during the Q&A. So we ask you to just use the question box as you see here. And if you raise your hand, well, we'll just ask you to put it back down and just put your questions in the box. It'll be easier for us to handle. And as mentioned, this webinar will also be recorded and shared with all registered participants and eventually posted on FAMIC website. So I'll now pass things on to my colleagues so that we can start the presentations for today.
Okay, thank you. The first topic we're going to cover today is the pneumatic grippers. So what these components are is a series of pneumatic cylinders. Well, we have them in the pneumatic cylinders family in the library, and they're a category of their own called grippers here. And they are, let's just look at them here. They are a series of grippers which are divided into two different categories. So we have parallel grippers and angular grippers. And then within each, we have double acting, single acting, normally closed, single acting, normally open. They are all quite similar in how they operate. So if we just look at, for example, one here, and we look at the component image, what we have is a piston with a piston area and a rod side area. And this is linked by a mechanism which will open or close the gripper fingers. Now, obviously, the parallel grippers, they open in a parallel motion. So if we look at the image here, you can see it goes from parallel close to open in this fashion. If we look at the angular grippers, similar type behavior, but instead of opening in parallel, they open at an angle here. They are all, so like I said, there's double acting. Each of these double acting cylinders actually has the same behavior, but the only difference between them is the symbol. So this one shows an external gripping, so the teeth or the fingers here are gripping on the outside of an object. This one would be gripping on the inside, and this can work in either fashion. The properties of these, so when we go to configuring one of these components, some of the properties you have here, you see we have piston diameter. We don't have rod diameter. And we also don't have a piston stroke, rather we have the finger stroke. So we define how far the fingers open and close, and then the software will calculate the equivalent piston movement here. So the other thing, so this is the basic data we have here. We also have the technical specifications. This is information you will get from the manufacturer spec sheet, additional to the finger stroke and the diameter. And this will tell you how much force the gripper can apply for different pressure levels. So here, for example, at 8 bar, the gripper can apply a maximum force of 120 newtons almost. And then depending on the distance of the object that it's gripping from the base, it can apply less force, generally speaking. So this is a parallel gripper. You see the angle or the slope isn't very, it's very, very shallow. So there's not much difference in distance and that one. So we have two tabs here for defining the curves. We have the internal gripping. So even though this one is showing as an external gripper, you can still define it to have an internal gripping force, but then the external gripping force as well. And this here helps us to determine, so based on the manufacturer data, we can calculate the area and the amount of flow and so on that the gripper requires. So if we go back to the data tab here, we can see that we don't have the rod diameter. So this is calculated based on the ratio between the two different tabs here. That allows us to figure out, what the equivalent rod diameter would be for that, for that ratio of forces available. The reason we had to do it this way is because in a lot of the manufacturer specifications, they don't actually give the rod diameter information. So we sort of made an assumption based on the difference in the forces that will give us a difference of area on the piston and rod sides. So this is for the parallel gripper. If we look at the angular gripper, we can see similar type behavior. The curves here in this case, because the distance of the object has a bigger effect due to, if we just look at the image here, due to the fact of it being rotating, the further away the object that you're grabbing is, the more force you have to exert, or the more torque you have to exert to apply the same force. So these are the angular grippers. So a lot of the data here is quite similar between the angular and parallel, but there are a few small details. For example, in the parallel, we defined a spring constraint and a spring stiffness. So here actually, even though this one has no spring on the symbol, you can apply a spring on either side, which doesn't change the symbol, but it will just add that behavior to the spring, to the gripper. And with this, you can apply a spring stiffness. So it will have an initial force required to start to move it, similar to the cylinders that we have already. And then the spring stiffness will be newtons per meter, newtons per millimeter. So this is linked to, so the displacement here is linked to the finger movement. So we apply the spring force directly onto the fingers. For the angular gripper, it was a little bit more complicated to link the spring force to a linear position. So what we did instead was just to set a spring constraint, which is the same, but then you can have the maximum spring force. So you just put the min and max force that is applied, and this is compared again with the curve data. So for example here, if we look at a data point here at 74 newtons, if you have a spring of a spring force of 10 newtons, for example, then your available force is reduced by 10 newtons. So it applies directly to the curves here. And that's it. So then some just a demonstration of how this works in reality. So here I have configured this gripper. I'm using the angular one here because it's a little bit easier to see the difference in some of the data points. But I've configured it with a spring constraint of 0 and a spring force of 100 newtons. And then I can use this graph here will show the movement, how far the gripper opens depending on the pressure that I'm applying. So here, if I look at, I have a gripping point in this gripper here of 100 millimeters. So that's the object I'm gripping is 100 millimeters from the base. And based on the data in the gripper, I was able to create this set of curves, which will show how far the gripper will open against the spring force for a given gripping point and pressure. So if we look at this here, for example, the gripping point of 100, 2 bar, we're able to apply, or we're able to open to 2.9 degrees. If we increase, say, the pressure here, we can open it all the way to 13 degrees. And if we change then here the grip distance, say let's reduce it to 50, and then we try the same thing again. So now we can open it much further because the object is closer, it's easier to grab, and we're able to open further against it. So this is just a demonstration to show the link between the grip distance and the force and pressure available. But This is not how you would normally use this kind of a component. This is just to show you just some of the parameters. If you want to actually use this, so let's just say you're emulating that you're grabbing an actual object. So you have something like this where the object, in this case it's the internal one, so you're grabbing an object which is on the outside of the component. This will apply a hard limit onto how far the gripper can open. So the gripper fingers will open until they reach the component, and then they will stop at that point. So if you wanted to emulate that sort of a force, what you would do is something like this. So you'd have a driving force curve of 0, so nothing is happening. And then once you get to the point at which you grab your object, your force will suddenly increase. And here you would need to set both force curves, so the extension and the retraction curve, you will need to set both. Because if you only set one, you can have some, it is not coherent with what the actual real world situation would be, but it would also cause some instability in the system. So here, if we do apply the activate the solenoid here to apply the force on one side, you can see that the gripper will open until it reaches the object, and it will, maintain whatever pressure you have on this side, and then we can close it. So this will calculate obviously the amount of pressure required, the position versus the pressure, and how much flow is needed. So if you're doing repeated cycles, and the amount of gas that you're consuming is an important parameter, then it calculates correctly the amount of gas based on the information that's available in the specification. So that's basically it for the grippers. The next topic today is the new mathematical blocks. So what those are is a collection of blocks. So we have a workshop here. If you have the license in your Automation Studio, you'll have a library here of blocks. What these components allow you to do is build a circuit using different calculations. So you can have different types of input, square waves, sine waves, or even just a cursor. You can use different mathematical operations, so the basic addition, subtraction, multiplication, sine, cosine, various operations that there are there. So we're constantly adding new components to this workshop. And in this current version, I'm just going to show you the new ones that we've added. So I'll start with the new adapter blocks. So again, these components are new in this version. We have previously had adapter blocks, and these are in this section here. So they're broken up into the different workshops. So if you want to create an adapter, a fluid adapter, so hydraulic or pneumatic, electrotechnical and mechanical. And just in case you're not aware of these, just to show you what the adapters are for, you can use them in conjunction with the custom component to create a whole new component. So for example, here I have a component which is called an air fuse. And if I open up this component, you can see I have one of these adapter type blocks, which will read from the circuit that you just saw, send the information to the different components, and then the output from that will be sent here in terms of a conductance value, which will then be used in the circuit here. So in this version, we've added a few different adapters. So one of them, these two here, they've added pressure source, so you can actually generate pressure, temperature source adapter as well. So you can see that there's different adapters here. So if you've been using these blocks before, and there's one or two different functions that you wouldn't have been able to implement, for example, we can now create reservoirs in the hydraulic or in pneumatic and accumulator, for example, or in the electrotechnical, we can do regeneration. So if you have a battery that's recharging, for example, that is something that is now possible. We've also added new input component types. So the first one here is a random number generator. You can create random numbers in using different distributions. So you can either have a uniform distribution or normal distribution, and depending on which type you choose, you can either select upper and lower bounds or mean and standard deviation. We've added a ramp. So this is, as the symbol suggests, It's a signal that's 0 for a certain amount of time and then gradually increases over time. We've added 2 impulse generators. So one is just a straight impulse generator where you can, in the properties of the component, set a time. So you'll have a 0 signal for a certain amount of time, then you'll have an impulse at that moment that you've specified, and then 0 afterwards. And then this one is the same, except rather than having it in the properties that you set the delay, you set it using a cursor. Next component here is a fairly useful one if you're creating your own components. This is a multi-curve graph. So what this allows you to do is to do an interpolation between different values. So this component takes 2 inputs, x and y, and then uses those inputs to determine a z value. So for example here, we're expecting x values between 0 and 100, and the y values here, we have 3 different curves here, so for 0, 20, and 40. So how this works, if I have an x value input of 50 and a y, let's just select 0 here and click on the curve here. So we have a y of 0, a y of 0, then our output will be 10. If our y is 20, so this curve here, we will have an output of 20. And then if my y is somewhere in between the two, we will get an interpolated value between those two curves. So just to demonstrate that, I just run the simulation. So I'll set my x to 50, my y is 0, and my output is 10. And if I set my y to 20, my output is 20. And if I go in between the two, you'll see the value varies accordingly. So this can be useful if, for example, you're creating a relief valve or some similar type component that has multiple curves, and you want to interpolate the values between those. The next component is a square wave generator. So this has different inputs and outputs, as you can see. So you can set the min, max. You can choose either to send a frequency value or a period value. So this you would set in the properties here, whether it's frequency or period. And the input then is interpreted accordingly here, and it will generate a signal based on that information there. The next group of components are different matrix functions. So most of these are, you either understand them or you don't. If you know what a cross product is, well, that's what the matrix function here does. Dot product similarly. You can do convolution functions. You can do then other matrix functions, for example, eigenvalues and eigenvectors. So you send your input matrix, it will give you both the eigenvalues and the corresponding eigenvectors. You can sort your matrix. So the values of the matrix you can sort by row or by column, increasing or decreasing. You can get the matrix size. So you can see all of these are showing the values from the previous time that we ran the simulation. Some of the others actually I'll have to run the simulation so you can see. But if we look at, this is our input matrix here, we can get the sum of the elements, the rank of the matrix, and the norm of the matrix. And then at the bottom here, we have 2 other matrix operations called the Hadamard product and the Kronecker product. So if you know what those are, you'll know what these functions do. If, like me, you don't, well, then you don't, but they do as the name suggests. Next group are some different mathematical functions. So the first one here is the inverse tangent. So this does, as you can see from the image here, given it an x and y coordinate, it will calculate the angle here, so relative to the x-axis. We have a reciprocal square root. So this is just a combination of these two components into a single component. It allows the code to run faster. So if you're doing a 1 over square root of x, you can use this. It should simulate a little bit faster. And finally, we have in this section a round component. So this rounds using many different, you can choose one of many different methods to round. So floor, ceiling, towards 0, away from 0, and so on, as you can see here. One possible use for this is if you're using a selector. So a selector is a component that has multiple inputs. You can choose from one of the inputs. It requires an integer value as an input. So you might have a calculation that's choosing one of a series of values. You need it to round to a nearest value, so you can use this component, so then that input will be compatible with the selector. The last section now is updated components. So these are ones that have existed previously, but we have added some new functions. So the first one here is the square root. And what the square root is now capable of doing is to accept complex numbers. So you can see here we have a complex number being generated. So its value is 6 plus 2i. It's calculating the square root and we're getting the result out. You can also use it to calculate the square root of negative numbers. So here we have a cursor that's generating a signal of 4 while it's calculating the square root of 2. If I reduce it to 0, you'll see if I plug it in directly, so the 4 going into the square root, it's giving me an error once I go below 0. But if I send that signal instead to generate a complex number, so I have just the real part, which is negative, the imaginary part is 0, as we can see here, then that you can calculate the square root of that and it will work just fine. Next component here is the derivator. So this is like I said, it's not a new component, it exists previously, but we've added in a filter cutoff frequency. So this helps with stability sometimes with the derivator, especially if you're doing something like where you're working with a cursor or something like this, where it's possible to generate, change the signal very abruptly. Something like that would cause a lot of problems for the derivator. So having the filter coefficient in there allows you to sort of smooth out those transitions, so it shouldn't be as unstable as it may have been in the past. And we now have this component which accepts matrices, so you can do the integral of a matrix. So that's it for all of the new mathematical blocks. I'll now pass you on to my colleague Abderraouf, who will continue with the rest of today's presentation. Thank you very much.
Thank you, Shane. So I will present the improvements we have made in the electrotechnical workshop. For this version, we have worked on several topics, such as lamps, which can be found in the electrotechnical IEC, for example, control, signaling device. So for this component, we have added LED type. So we have added AEC LED lamp and DC LED lamp. Also, we have developed for each component 4 simulation models. So if you double click on the component here in simulation model, you will find four models depending on the informations you can get from the data sheet. You can choose the appropriate model for you. So we have just a model for which use the voltage and power. We have a model with the voltage, power, and flux, and voltage, power efficiency, and voltage, flux efficiency. If you click on one of these models, you will see that the parameters you can set on the model will change according to the chosen model. So for the moment, this modification are applied on filament lamp, IC and DC LED lamp, rotating light, and the pilot light energized by a built-in transformer. So as an example, here we have 4 models of lamp. So you can see here we have different symbols. We have rotating lamp, we have filament lamp, NEMA filament lamp, and IEC LED lamp. So if we double click, we can find that here we have I have set 10 watts as the power to be consumed by the lamp when powered with the rated voltage, and for each lamp we have set a value. For example, for this LED we have put 3 watt. So if I start the simulation and I measure the consumed power by a wattmeter, we can see that the lamp is consuming the same amount we have set in the parameters. In the next version, let me stop the simulation. In the next version, these modifications will be applied on this type of lamp. So the modifications will be applied to pilot light energized by built-in transforming flashing, pilot light, single tower, beacon flashing, and other samples of light. That's one thing. The second thing, we have worked on the encoder and decoders. So for this version, we have added many types of encoders. So for example, Hall effect sensor in two types, 90-degree and 120-degree. The solver, the endictocene. We have improved also the incremental encoder. So for example, if you double click on any type, for example, for the endictocene, you will find here the appropriate parameters that you can set to do the simulation. For example, in the incremental, we have the pulse per revolution, the rated power, the rated voltage, and so on. So in this version, we can assign the output signals like A, B, and Z. If you go to the variable assignment, you will find this variable here, so you can assign it to other variables, so you can use it for motor control or any type of application. You can also display the absolute position, the rotation, the direction of the rotation of the motor, and also the speed and the absolute position. For each type of this encoder, we have developed a decoder. So as you can see here, this decoder and encoder can be found on control, sensor, speed and position. Here you can find the encoders, and for the decoders, you can go to black box inputs, and here we have the decoders. So the decoders will read the output of the encoders and give us the speed, the angle, and the absolute position, and the relative angle. We can assign this by variable to use it in motor control. So to see an example, here we have a circus with a DC motor, a slider to change the resistive torque applied on the motor. We have incremental decoder. If you can see here, I have put the pulse per revolution 100. I have a decoder, and just to mention that in this version for the DC motors, we have made three improvements. The first one is the calculation of the power balance in real time. So if you double click on the motor and go to this section here, you can see that we have added all the parameters we can calculate in real time, like efficiency, field copper loss, input power, output power. If I start the simulation here and I start the motor, you can see that these parameters are adjusting according to the environment. So if, for example, I increase the resistive torque, you can see, for example, that the efficiency is increasing also. All the parameters are changing. Okay, and the second thing, we have added the effect of the temperature on the motor. For example, here, if I take plotter and I drag and drop my motor, here I can plot the temperature. So if you want to do this simulation, you have to go on simulation options and activate the option of thermal evolution. If we start the simulation, here the motor has exactly the temperature, the ambient temperature of the environment. If you start the motor, you can see that the temperature starts to increase until it will be stable in the next seconds. So this calculation of the temperature depends on the internal parameter of the motor, like the thickness, the thermal resistance, the thermal conductivity, the contact surface. So we can change this if we want to change the behavior to the motor reaction to the environment. Another thing we have added in this version is the type of cooling for this thing. So we have added three type. Excuse me. Okay, we have added three type. The first type is the free convection. The free convection is when we don't have any active cooling on the motor. The second type is self-circulation. If we choose this option here in the power dissipated to cool the motor, we have to set the power we are using to cool the motor. By the way, the self-circulation, that means that the device we are using to cool the motor is internal, like a fan inside the motor or something. So we have to put the power of this device in this parameter. The third type is the mounted independent component, and this when we choose this, that's mean that we are using an external device to cool the motor, and in this case we have to link it by this variable here in variable assignment. So we have to assign this variable to this one, and this one take a dissipated power as input. So we have to link the dissipated power by this device to this variable. And so here, just to come back to the encoder and the decoder, here if I take a plotter and I drag and drop my encoder, here you can see that I can plot A, B, and Z. So if I start the simulation, start my motor, you can see how the A, B, and Z are working. And if I change the direction of the motor, for example, you can see the switch between the B and the A. And for another thing, if I plot the real angle of the motor by dragging and dropping the motor on the plotter, and the relative position calculated by the decoder by dragging and dropping the decoder on the plotter, we can see that the two signals match and the decoder is working well. Okay. So for this version we have worked also on the current transformer. So for the current transformer we have made two simulation models. The first one is the simplified model, and this one allow the use of the parameters we find usually on the data sheets. For example, like the rated primary current, the rated secondary current, the security factor, maximum thermal current setting. So this model, if you give it a primary current, he will give you a secondary current, which is the primary current multiplied divided by the ratio. If I start the simulation here, you can see as an example here in the input I have 4.6 ampere. The output is 2.3 for the ratio 2, so that makes sense. And for the security factor, you can see if we exceed 5 times the secondary current, our transformer will saturate, and if we exceed the and you can see if we exceed the thermal current overload. Here, if I bring my message explorer and I reduce the resistor, we will have a warning message that indicates that we have exceeded the maximum current between the connector P1 and P2. And second for the second model, for the current transformer, we have developed a theoretical model that allow to see the more deep phenomena relating to the internal construction of the transformer. So in this model we take into consideration parameters like saturation magnetic flux, resistive load, remnant flux, and other parameters. So with this model we can see some phenomena like the saturation. We can plot the the graph of the saturation. So we can see here the form of the graph when the current is is when the current is too high, and we can, for example, compare between two parameters. Like here we can see that when the remnant flux is higher, the current transformer will saturate faster. And also for this version, we have developed an option. So if I go to Tool, Communication Manager, and I go to CAN, so here we will find that we have a new option called Bus Speed, which allow us to choose which speed we are using, when to use in the communication. Also in SR2 we have made improvement on the illustrated library also. So if I click on the open library, here we have developed we have made the changes in two libraries. The first one is the North America Residential Electricity, and here we have added a new category which called Blueprint. So this category allow us to design in architectural plans and put electrical details. So in this category we have here the component which can allow us to design the plan, the architectural plan, like frame, doors, stairs, kitchen, bedroom, appliance, bedroom, large, frame, doors, stairs, and others. Uh, to show you all the type of components we have added here, you can see that in the electrical side we have added many symbols like switches, wall outlets, ceiling outlets, receptacle outlets, which can be found here. So here we have for every category we have two sizes, small and large. So here that's okay. And the second thing we have made also in the motor control and renewable energy, we have added a new category in motor control, passive components. So here we have added optocouplers, thyristor, transistor, diac, and triac. So for example, if you double click on the optocoupler, here you can find the parameters you can change, and they are taken into consideration. These parameters, for example, for the triac, we take into consideration the gate trigger current for the four quadrants, the holding current, and the gate voltage. So that's for the SR1, and I want also to mention that for SR2 we will make an improvement on the solenoid. So for the solenoids in SR2 we will have many types, on-off DC, on-off AC, with and without protection. We will have also solenoid with rectifier, proportional DC solenoid with and without protection, and also proportional solenoid with the integrated control. Also, we make this component which reduce the absorbed current in the starting, and also the proportional solenoid driver to pilot the solenoid. And this pilot have many options, like dither function, input signal, different input signals, PWM, current, analog voltage, free current. So we can set our value. For example, if I choose free current range or free voltage range, I can myself put the values I need. For example, the same thing for the output signal. And also we can change the PWM frequency. We have the ramping option. We can set activate or deactivate the ramping, and modify the ramping down time, the ramping down up, and we can modify the gain, for example. So we have many options here. Uh, as an example here, I want to show you if I pick this solenoid, with the integrated control one. Here I can change the consumed power, the rated voltage, uh, the the signal type. That the solenoid can read from the external controller. So here I have to put a signal like here I choose from 0 to 5. I can also configure my controller. Here as an input I will set 0.10 volt. For the output it's 0.5 volt, so the solenoid can move accordingly. So no ramping function. So here I can change the input of the controller with this slider from 0 to 10 volt. And here I have to go to my hydraulic distributor, click on the coil, and link it to the output signal, this one. So here I made the link, and now I will start the simulation. And here if I change the input, we can see that the distributor is moving accordingly. So here I can change the position of the distributor by changing the input voltage on the controller. Okay. Also, in this improvement, we have added the effect of the temperature on the solenoid. For example, if I go to another example, here, if I double click on my component, here, if you go down a little bit, you will find a new section. The new section have many parameters, like the material of windings, the specific heat capacity, temperature coefficient of the material, heat transfer coefficient. So all these parameters will be taken into consideration to simulate the temperature of the solenoid. Okay, so for example here, if I take a plotter, and I drag and drop my solenoid. So here, for example, I set my first the initial temperature to be 25, for example, and I start my simulation, and I close my my switch, and I can see here that the temperature of the solenoid is bigger than the ambient temperature we have set because of the dissipation. So if I increase a little bit my ambient temperature, let's like put 35, and we can see here that the temperature of the solenoid is moving up until it achieves a stable level, and it will be more than 35 because of the dissipation, which is taken into consideration also. So uh, in this context, we can also see the effect of the temperature on the solenoid. Like if I take a new example here with a proportional solenoid, it's the same thing as the example I have uh, made for the controller. And here I have to go to simulation options, and activate thermal evolution. And here this solenoid is linked to the hydraulic circuit. I will set my first temperature to be 25, and I want to my output signal to be displayed. Okay, and so just a second here. Okay, okay, and here I have to start the simulation. And here we can see that we have a position. The output is 55.48, and now if I change the ambient temperature, for example, you can see that the position, the output is changing, which will make this distributor to change position. So maybe in this case the position is the change is not significant, because the change of temperature is not significant. But if for example, if we go from 35 degree to 100 degree for some reason, we can see that the change in the output will be significant. Okay. The last thing about the solenoids is in the let's just go to this model here. If we double click on the component, we'll have that for each solenoids we have 3 simulation models. We have simplified circuit, equivalent circuit, and dynamic model. For the simplified model, we take into consideration the rated power. So when we activate our solenoid, the power that will be consumed by the solenoid will be the rated power. If we choose the equivalent circuit, here we can set the values of inductance and resistor for this solenoid. And the dynamic model take into consideration in this type for DC on off the rated power, the rated voltage, and the time constant to help defining the transitorial regime in the first second. But for example, if we take another type, for example for the AC model, here we will find that we have also three models. So for the simplify circuit, we will take only the holding power. For the equivalent circuit, we can set the inductance and the resistor, and for the dynamic model we will be considering the holding power and the initial power. Okay, if I take an example in the simulation, and I want to simulate the current of the three models here: simplified model, equivalent model, and dynamic model. And I start the simulation. Okay, here the first graph here in the green, it's the dynamic model. So we can see here how the transitorial regime can behave in the first second. If I took, for example, the simplified model and I close the switch, here we can see that in the simplified model, the current go directly from 0 to the maximum current. And the last example is the equivalent circuit. So the equivalent circuit, it's an RL circuit, the blue one. Okay. So if I stop simulation, zoom in a little bit, we can see here that the solenoids behave as a RL circuit. So that's it for the solenoids. And that's all for the electrical part in this version and in the version SR2. Thank you.
Thanks, Shane and Abderrahuf, for those presentations. We'll now be moving on to the questions portion of the webinar. So I'll remind you again, if you have any questions, just put them in the questions box, and we'll be sure to answer them. Okay, I think we have a first question here. Is the force applied by the grippers the same across the full range of motion? Can toggle type grippers be modeled?
I assume that's for me, Bruno.
Yeah, that's that's part of your presentation.
Sorry, I'm just going to show my screen again. Do you have to make me presenter, Bruno?
Oh, okay, I should be able to. Let's see if I go to attendees. I think you should be able to grab
I can change it to myself. Yeah, sorry.
There you
go. Okay, so just to clarify what that is, let me just, where's my, I have a little example here of the kind of how the gripper works in reality. So in the background, you have some sort of a mechanism like this, whereby as the piston moves, it moves a sort of mechanism that we don't know necessarily, but it moves linearly. So depending on the position of the piston here, the grippers will open more or less the same amount. So if the piston is at the base and it moves 1 millimeter, this will move a certain amount of millimeters based on the lever ratio. That's the kind of operation that we have. So this is not the toggle type. The toggle type here is something where it's a bit more extreme. So for now we don't have these, but if you look at, say, the position of this piston here, you can see that if the piston moves here, the gripper fingers won't move very much. So the movement here is not linearly related to the piston position. So this is not something that we can currently do, but if there's a request for it, we can add it in a future version. We decided that the majority of the grippers on the market have a more linear behavior, so we just implemented that for this first round.
Good, thank you, Shane. We have actually another question related to the grippers, so I'll ask you that now since we're on the topic. Yeah, so these grippers are all 2-finger grippers. Can the model be used for 3-fingered grippers?
It can, but you would need to make a slight modification. So just let me go back to my main page here. So the way we calculate here on the technical specifications based on the information here. So this is the grip force on one finger. So on each finger normally. So in this case, we have a single finger. Each finger is giving me a force of 120 newtons, more or less. If you have 3 fingers, then you would need to modify the curve here to account for the fact that there's 3 fingers. So if your specification gives you 3 fingers of 120, what you would need to do is say make 2 fingers of 180. That would give you the equivalent force and equivalent pressure on the piston side of the, the pneumatic side. Will link it correctly to the gripping force. But the specifications are similar, so the same types of curve apply, whether it's angular or parallel. So you will be able to take the same data and put it in, you just need to tweak it slightly.
Very good. Yeah, related to your presentations as well, Shane, we have a question about the math workshop. What new blocks are planned for the next version?
So some of the new ones are, we have different types of signal generators, delay blocks, and we're going to increase the compatibility of blocks with complex numbers. But these are just some things that we have already had requests to add. As always, if there's any other blocks that people are requesting, we can add those. But for now, that's sort of a small overview of what's to come. But we're always happy to get feedback and requests for different things.
Very good, thank you, Shane. Okay, we have a couple of questions here on the electrical, so I'll address Abderraouf for these ones.
Yes.
Abderraouf, you're with us?
Yes.
Okay, so one of these questions is, are these improvements applied to all motors?
Actually, the improvements are only applied to generators, DC motors, and DC machines, but they will be extended in the next version to all the other types of motor.
Okay, thank you. Another question here. How can encoder output signals be used?
Actually, usually we use them to control motors. So for example, in the next version, we will support the BLDC motor, and the control of BLDC motor are based on the Hall effect signals. So they can help us to determine the relative position, so we can adjust our output signal from the controller.
Okay, very good. I think we have one more question here. Are diacs and triacs available in the generic library?
Currently, we have only a simplified model in the illustrative library, but the development of these models are planned to future versions.
Okay, thank you. Let's see, I don't believe we have other questions. So with that being said, I think that that kind of covers it for today. I'm going to just share back my screen really quickly here. If I can take back presenter and then show my screen. Okay, so you should be able to see my presentation again. So yeah, just to mention, so again, the video for this session will be available for anybody who's registered. You'll be able to access to it. And the next webinar that we have planned will be the final webinar for this series, which will cover some of the new workshops available in Automation Studio, so the P&ID and the robotics. So we invite you all to attend. We hope that the presentations today have been informative on some of the new capabilities available in Automation Studio 9.0. If you have any other further questions that you might not have asked during this webinar, but that come up, feel free to reach out to us anytime. We'll be happy to assist you. Thank you all so much for attending this webinar, and have a great day. Hope to see you next one.